Hello, and thanks for watching our final presentation. We are the Southgate CEHAT clinic team advised by Professor Madero. Our liaisons are Samir Patel, Liz Ruiz, and Victor Ferrer. Our clinic project is community-based, so it's important that we offer some background to the community we're working with. The city of Southgate is in southern Los Angeles, near the intersections of the 710 and 105 freeways. There are just under 100,000 residents, of which 95% are Latinx. It's important to note the demographics of the community, not only because it affects the users of our products, but also because of environmental justice concerns. A historically industrial city, Southgate is subject to higher levels of pollution from industrial plants. Within the city limits, there are 3 Superfund sites, which are locations that the EPA has designated as among the most contaminated land in the country. In case you don't know, the EPA is the Environmental Protection Agency, which is the branch of the U.S. federal government that is tasked with all environmental concerns. Southgate is also home to 2 oil and gas wells whose toxic products and byproducts pose a risk to residents. In addition to contaminated sites, Southgate residents are also subject to high levels of pollution from the transportation industry. The 710 freeway alone brings over 20,000 diesel trucks through the city every single day. Train traffic is also a source of pollution, as 30 to 40 freight trains pass through the city every day by means of the Alameda Corridor. On top of all that, being in Southern California, Southgate is subject to intense fire seasons as well as pollution from the greater Los Angeles region. All of these factors combined puts the community of Southgate at high risk for environmental health consequences. This leads me to introducing our sponsor, the Community Environmental Health Action Team, otherwise known as the CEHAT. Founded in 2013, the Southgate CEHAT is a community organization comprised of city residents, business owners, community activists, and members of state, local, and federal government. The CEHAT researches environmental health concerns in the city and works with the EPA and regulators to improve conditions in Southgate. Another large focus of the CEHAT is education and outreach with the local community to bring awareness to these issues and inform community members how they can stay safe. The current focus of the CEHAT is the poor air quality in the city. Air quality is affected by compounds such as ground-level ozone and nitrogen oxides, as well as particulate matter, which ranges from 1 to 10 micrometers in size. PM 2.5, which stands for particulate matter 2.5 microns in diameter, is the largest contributor to air quality measurements and is of interest to the CEHAT. This size of particulate matter is common in emissions from transportation and power plants, and is particularly dangerous because it has the ability to travel deep into our respiratory tract and lead to health consequences. The concentration of PM 2.5 can be directly measured and then used to calculate an AQI, which stands for Air Quality Index. The Air Quality Index is the U.S. national standard for measuring air quality. We use EPA formulas for converting from PM 2.5 to AQI. In 2019, the Southgate CEHAT received a grant for 20 purple air sensors, which are an affordable air quality sensor option costing around $250. These sensors are great for the CEHAT because they are easy to install and maintain, as they only need Wi-Fi and a power source. Despite their low price, they actually measure PM 2.5 concentration with reasonable accuracy. The EPA has even started integrating readings from purple air sensors into its own fire and smoke map. These sensors are essential to our project, since there is no EPA-regulated sensor within Southgate city limits, so residents currently have no local data to inform their health decisions. The goal of our project is to positively impact residents of Southgate by providing information, analysis, and education on air quality in the city. We hope to help residents make more informed decisions about their own health and to provide regulators with concrete information to use when creating policy. Our work falls into 2 categories: an online air quality dashboard and reproducible data analysis for the CEHAT. I'll now turn it over to Hillary to talk more about our analysis work.
Thanks, Amber. For our data analysis work, we wanted to give the CEHAT members ways to visualize and analyze the purple air data. So, we decided to make an interactive report using R Shiny so that the CEHAT members can reproduce the results for future data. Here's our report. The first thing the app asks you to do is upload a purple air CSV file. Then it asks you this question. The format of the data changed after March 30th, so it's important to specify when the data is from. Then you confirm what sensors you'd like to include. For the purpose of this demo, I'm going to include all of them. Then the first 10 sensors will populate right here. Notice that you have an option to generate a report. The report contains all of the graphics that I'll be showing you in this demo today. Next, we have the summary statistics page. For the purpose of this demo, I'm only going to go over a few of the graphs. These first 2 graphs show the hourly and daily averages of PM 2.5 for the month of April. Down here we have some quick numbers of the percentiles for the PM 2.5 ratings. This graph shows the daily highs and lows of the PM 2.5 readings for the month of April. If you hover over the circles, it'll show you more information. These graphs show you 8-hour averages for 2 different time periods so that you can compare them. And down here we have diurnal patterns, which are patterns that happen every 24 hours for the average, peak, and range of PM 2.5 values. Next, we have the sensor summaries page. It's divided into 2 sections, the network-based observations and the single sensor observations. The first graph shows the total count of PM 2.5 readings by sensor and their corresponding EPA categories. Down here we have graphs that show how many PM 2.5 readings go over the median or under the median. This legend specifies how much the counts go over or under the median by. Next, we have the single sensor observations. This section contains plots that tell you more about the readings for individual sensors, which you can select in this dropdown. Similar to the network-based observations, we have a category of readings for an individual sensor. We also have the daily highs and lows for PM 2.5 readings, and a histogram that tells you more about the distribution of the high values for our selected time period. Next, users have the ability to compare the PM 2.5 in Southgate to the PM 2.5 in other communities in LA. First, you must upload a CSV file of AQMD data, which you can find at this website. Then the app conducts t-tests on these data sets and finds the p-value, as well as which city has the worst air quality. Next, we have a box plot, which divides the PM 2.5 readings for both cities into 5 sections: the minimum, the first quartile, the median, the third quartile, and the max. Here we have a side-by-side bar chart that shows the daily averages of the PM 2.5 values with the legend that indicates the cities that you are looking at. Next, we have the interpolation and sensor placement page. I'll pass it on to Lieutenant to tell you more about this.
Thank you, Hillary. As Hillary mentioned, the final tab of the analysis application displays the interpolation calculations for a network of sensors for a given timestamp. The interpolation method that we've implemented in our app is known as ordinary kriging. This method of spatial modeling invokes a semi-variogram, which is a kind of model that indicates spatial correlation within our data. In short, a semi-variogram models the relationship among sensor locations to indicate the variability of the measure in relation to the physical distance of separation between locations. In our case, it shows the variance in readings in relation to the calculated distance between all pairs of sensor locations. In our app, ordinary kriging takes the semi-variogram model and uses it to apply weights to the measured values in the data and estimates values at locations without sensors. Each set of ordinary kriging calculations provides 2 important pieces of information. First, predicted PM 2.5 values across Southgate, and second, the variance and/or standard deviation of those values. Thus, CEHAT gets additional, albeit estimated, coverage, as well as a measure of where they should deploy more sensors, since better coverage reduces spatial variance. The interpolation features of our app provide CEHAT with the ability to determine the typical air quality at sensitive locations, like schools, parks, medical clinics, and senior centers, where they may not be allowed to place sensors directly. The diagram to the right shows one such visual. This map uses the PM 2.5 estimates from the kriging computations and displays the pertinent calculations to display the AQY based on the estimated PM 2.5 values at and around identified senior centers in Southgate. As was shown in the app, there are detailed descriptions that explain each of the calculations and visuals on each page. On the interpolation page, these descriptions explain what kriging is and how CEHAT can use the variance and prediction calculations to either restructure their network around these sensitive locations or to advocate for more sensors. I'll now pass it off to Adam on the web development side to talk about how we've structured the website and technical accessibility.
Thanks, Lieutenant. The main way that members of the community of Southgate at large are going to interact with our project is through our air quality dashboard website, which is available on the internet through the link provided or by scanning the QR code. The website was built using the React framework, and just like our analysis application, the source code for the website is available open source on GitHub for other communities to build off of our work. Since the main goal of our website is to clearly and easily communicate the air quality in Southgate, when people visit our website, they're greeted by a map of Southgate annotated with the sensors and their current air quality readings. Clicking on a sensor puts the current AQI at that sensor in context, using a gauge to provide a sense of scale along the EPA's Air Quality Index scale. We also provide a graph of the air quality at that location over the past 24 hours, so that visitors to the website can get a sense of how the air quality at that location has changed. Recognizing that members of the Southgate community are frequently on the go, maybe they work outside, it's important that air quality information be accessible wherever they are. Therefore, throughout the development process, we've always been thinking about the mobile experience, working hard to make sure that our website is user-friendly even on smaller screens. Users can even install our website as an application that runs outside of the browser thanks to the Progressive Web Application Framework. Air quality can be a complex topic, and so we provide comprehensive information on why air quality is important to our health, what it means, and how we can protect ourselves when there's poor air quality. From user testing feedback, we know that it's important that we provide a definition of AQI frequently throughout the website, so we also have helpful tooltips throughout the website to redefine AQI for people. We also provide information about how people can get involved with the Southgate CEHAT so that our sponsor can get more community engagement. As a community-oriented project, it's been super important to make sure that everyone can use our website. Therefore, we've kept a really broad definition of accessibility in mind throughout the project. In perhaps what is the most typical sense of web accessibility, we've considered low and no vision users of screen readers by adopting the Accessible User Interface Framework Chakra. Chakra has helped us keep keyboard navigation and alternative text front of mind throughout the project. When we tested our website using screen readers, we noted that we've made significant strides towards accessibility. Unfortunately, the mapping software we're using isn't super screen reader friendly, meaning there is room for additional improvement in this area. For users with color vision difficulties, the EPA designated color scheme of green, yellow, orange, red, purple, and brown is not super user friendly, so we've provided a way for users to opt into an alternative color scheme that is more color vision difficulty friendly. We also know that Southgate has a large Spanish monolingual community. Therefore, we've used the React I18 Next library to help us provide a Spanish version of our website. You may be wondering, how do we get the translations for the Spanish version of the website? Well, many of us on the team have learned Spanish, and some of us are even natively bilingual. So, we have written the translations ourselves, going through a multi-stage review process both internally and with our liaisons. All of this has been super helpful to help consider all users of our website, but we wouldn't have users of our website if we didn't have quality air quality data. So it is now my pleasure to pass it off to Carson to describe to you how we get our data.
Thanks, Adam. Here's an overview of our original data pipeline. A quick note that the acronym API just refers to a way of getting data from another website. So first, we got our sensor readings every 2 minutes using 2 different APIs in Purple Air, and we stored each of these readings in our historical database. Then, every 10 minutes, we recalculate the AQI for each sensor, using the readings from the last 12 hours. This AQI calculation process comes from the EPA. Each Purple Air sensor has 2 particulate matter sensors called Channel A and Channel B. When data cleaning, we check that the 2 PM2.5 readings for each sensor have not diverged, which can indicate sensor malfunction. We then apply the EPA-provided correction value for Purple Air sensors, since Purple Air sensors tend to overestimate PM2.5 values, and the correction factor depends on the current humidity. Finally, we calculate a weighted average of these readings, where more recent readings are weighted more heavily. We then calculate the nowcast AQI, and this is the number that is displayed on the website. Unfortunately, we ran into 3 problems in the spring semester. First, Purple Air deprecated their original API rather suddenly. Second, we were sending too many requests to ThinkSpeak, which was causing us to get back errors and miss some sensor readings. And finally, our database reads in the calculate AQI step were too high and costly, and since we wanted to make this website as low cost as possible, this was a problem we needed to address. To address the first 2 problems, we transitioned to a new Purple Air API. Overall, this was a positive change that made the entire process more scalable and efficient. However, this introduced a new problem, a different data format. Instead of including the readings for channel A and channel B for each sensor, we can only access a confidence value that Purple Air provides but does not document. This was a problem because we used those two readings in the data cleaning process, as I just described. So after much correspondence with Purple Air, we were able to determine how to replicate most but not all of the data cleaning process from before, a concession that we had to make. And finally, we also started using a circular buffer to store the most recent 12 hours of readings. Essentially, this means that every 10 minutes, we read the database once per sensor, instead of reading the database 360 times per sensor for each AQI calculation. As can be seen from this graph, using a circular buffer was a huge success. Our writes to the database were doubled, but our database reads were dramatically reduced, which significantly reduced our database costs each month. Finally, I'll show the website admin interface, which allows CEHAT to manage the sensors and the historical readings. From this panel, admins can see the current status of the sensors in the website, including the last sensor reading time and any errors that a sensor is having. There are many reasons that a sensor might not be functioning, so this helps admin users determine if they need to reach out to the sensor host to reconnect the sensor to Wi-Fi, or if the sensor has malfunctioned and they need to reach out to Purple Air to replace a part. Additionally, from this page, admins can download historical data in the format expected by the math analyses described by Hillary and Latenna. This allows the CEHAT to continue to run these analyses with new air quality data, which is especially important given the timeline of our project. We have been gathering data from our sensors since October, but air quality is often much poorer in the summer months, which is after our project ends. Since the website will continue to collect sensor data, they will be able to use the tool developed by Hillary and Latenna to analyze the air quality of the summer months. Additionally, through this panel, admins can delete old sensor data, since data storage is not cheap, and we're collecting new data every 2 minutes. One of our goals for this website was to make the cost as minimal as possible for the CEHAT, so this function is critical. Overall, this admin panel allows the CEHAT to continue this work as our project ends.
Thank you for that, Carson. While we've completed the main components of this project with all the functionality that we'd hoped to provide, there are a variety of areas in this project that could be expanded upon. On the Community Air Quality Dashboard side, CEHAT was interested in integrating the interpolation calculations, which were shown in the data analysis app by Hillary, into a map of Southgate so that they would have real-time access to these calculations. CEHAT was also interested in a crowdsourcing feature which would handle complaints or reports from community members about odorous or airborne pollutants and public events that would affect the local air quality, like controlled fires. Additionally, CEHAT wanted the ability to alert the city about extreme air quality via text to residents and banners on the website. On the data analysis side, CEHAT and our team was interested in being able to forecast future PM2.5 values from the data, identify correlations in the data, and compare the air quality in Southgate to other locations. Of particular interest were correlations between PM2.5 and the rates of asthma and other respiratory diseases, and correlations between PM2.5 and other pollutants like ozone or sulfur. Similarly, comparing the PM2.5 in residential areas to non-residential areas, comparing PM2.5 across census tracts, focusing mainly on income level, and comparing PM2.5 in green spaces versus industrial areas were all of interest. Handling other sets of data would be key to implementing this in the data analysis app. If at any point CEHAT decides to revisit this project and expand upon it, these avenues would be the most logical and immediate. With this, we conclude our presentation. Thank you all for listening.